Hi everyone, today I'm going to present our final project, the social media oriented image caption with vision language models. So we were gonna start with background introduction, then talk about our dataset, our methodology, what we have for the modeling, and then how we improve the modeling section. Uh, we'll end with our result evaluation. Um, so let's begin with the motivation behind our project. On Instagram, captions are not just literal text. They're often like full of emotions, emojis, and then personal touch. So most traditional image caption models only generate plain text, which doesn't match the real requirement in our real life. So in this project, our goal is to generate captions that makes people feel authenticate, just like the real human being write for their Instagram post. So to achieve this, basically we fine tune the belief model or dataset, and then let's go to take a look at the dataset first. Uh, for this project, we use the Instagram image with captions dataset, which contains over 13,000 real-world Instagram posts. So as you can see here, each entry include a photo and then a caption written by the real user. So why we choose this dataset, or what makes this dataset ideal for our project? So this dataset has very high stylistic diversity. So the captions often features emojis, hashtag, and then informal language. So this pink is a good choice because we do want our model to generate expressive and then, social media native captions, like human being would write. So we before started, we perform a small cinema analysis on our captions. As you can see here, about 33% for captions were classified as positive, and the rest are negative. So this suggests that people tend to be more, direct or positive when sharing on Instagram. We also do some simple topic modeling. As you can see here, we found that the dominating topic here resolve around the themes are like celebrations, gratitude, and relation. So most of them are, the good part for the life. And then, as you can see, the largest topic cluster, topic one, have keywords like birthday, happy, same like birthday, and you and love. So this reflect how people express their joyful feelings when post. Another interesting thing we can see is document-wise topic modeling. So as you can see in the bottom left, it's actually very interesting. So uh, the emoji only posts form their own distinctive clusters. So it's really far away from all the other clusters, which suggests that emoji function semantically differently. So it doesn't really require accompanying text or like context to express their meaning. Then that's, I mean, we do understand how it works because, like, like a smile face means good, or cry face means sad. So it doesn't really require the context. It is the context itself. So that's one of the funny things here we found. As we take a look in the dataset, we now go into our modeling section. So let's talk about BLIP. So what is BLIP? BLIP stands for Bootstrapped Language Image Pre-trained Model. Basically, it's a transformer, so encoder and decoder. Uh, the vision encoder you can see here, it extract patch level features from the image, and then the text decoder also on the right. So it output task. It do condition have conditional based on the cross um, attention. So by through the cross attention, like two models can talk with each other, and then it'll be super useful in later section. We'll talk about it. Okay, so the first issue we got in trying to tuning the model is that it takes super long, like 200 hours for one epoch. That's too long, and we can't really take that much time. and we don't have the time. So one key optimization we made is like we separate encoder and decoder during training. Uh, because the wish encoder is super hard and then very computationally expensive in training, so we just freeze it and then we cache the image embedding throughout the whole training process, and then we only tune the encoder section. So this simply result in a massive speed up in training time, and then with no sacrifice in training quality. And we will see how good like the optimization is in the later section when we look at the data table. And then another optimization we introduce is we use LoRa adapt adaptation. So let's say LoRa, as you know, uh, we will not go into super detail about how LoRa works. Just saying like instead of updating all the weight in decoder, we insert a low rank adapter, like basically two small matrix into the query and key, and then the value matrix for the last four layers. And I mean, there is some good sides. Of course, there is some good sides. That's why we choose it. So it dramatically reduces numbers of trainable parameters during the training, and then it reduces the time for back propagation, and then the actual storage cost. So it makes training more efficient. But we also observe a trade-off between the speed and performance because it makes our model, trainable part for the model become simple, and we will discuss it later. Okay, so here's the analysis part. As you can see, four parameters fine tuning on the four dataset, which is the first row, and it's feasible. It takes like 200 hours. We didn't redo that. We just take some experiment and do the theory analysis. And so there's two main optimization we did here. One is we're sampling the dataset. Another one is we freeze the encoder part, only train the decoder. It cuts the train time to under just 10 minutes, as you can see, like just 80 minutes. So it's super fast. And then finally, we do use LoRa. But as you can see here, although the LoRa also speed up the process, and then but one thing happens here is like it all leads to under fitting because the model became much simpler, and that's not what we want. So we will use our this setting, the last resetting. So the cache embedding decoder only tuning. This setting as our final model to compare with our baseline. Sorry. So how do we evaluate our the final model or compare it with our baseline. There are multiple ways to evaluate the quality for and task output here. Like this kind of use case, you can use Ingram, you can use Blue, and then BRE is another uh, testing by method. But here we choose BERT score, which measures semantically similarity by comparing text contextual embedding of tokens. Basically, we have another BERT encoder and a you know encoding the ground truth, the baseline output, and then the training model output all into the same embedding space and then compare them cosine similarity. However, the result shows here doesn't really look good because the baseline model achieved a first score like 81%, and our final model, the training model, is also like 81%. Doesn't make much difference. So it just says like our training is useless and make no contribution in this test. I Some people may feel so, but like we don't think so. So to better understand what happened or like why it looks like this, or just go into more detail of our result evaluation, we further perform an qualitative evaluation. So basically, we grab some example, not just three. Actually, we did a lot, but like these three are most very representative ones to see whether our the train model performs better than the baseline. So let's now look at a few example here. So we can see the clear patterns. So the ground truth captions are highly personal, like a real human being doing, and the baseline model often just trying to describe the video sense. It's just like plain text or description, and doesn't it doesn't sound interesting. And our training model, on the other hand, then produced captions are very, emotional, and then really looks like, I mean, it's kind of like what human being would write. So, for example, in the first image, the baseline Hilarious says, like, stood in the flips, and then our final model says, I love it so much. And the second one, uh, so baseline only says are taken with ins, and our baseline says I'm so excited to see. I think this is the most impressive one for me. The train model says I'm so excited to see you at my next Disney movie. It feels like real human being alright, right? And then for the last one, uh, instead of just saying inside, I mean parrots, or the final model says I love this little guy so much and so cute. So this is another good example for our model does learn how to write Instagram style or like real human style Instagram captions. So this also shows that while semantical metrics doesn't shift that much, like what we can see here, the metric doesn't change that much. It cannot show a significant improvement, but actually, the human-like quality for the captions does improve dramatically during our fine tuning. So, just to wrap up what we have done for our project. So, first, we build an efficient caption generation pipeline that adapts the Blink model to generate Instagram style caption. That's the first thing we do. And then the main optimization we have is we freeze in the encoder, caching embeddings. We also use LoRa, although it doesn't really works well. We might need to some other strategy to improve it. And then we first use like first score to prove that our model does make a good job after the training. Although it doesn't looks good, but we also use qualitative result. This one that shows better, shows like our final model doing better. And then going one step forward, we hope to add prompt control and then, explore better emoji handling to build a more robust and pipeline for caption generation. That's all we have for our final project. Thanks for your listening.